Let's say we wanted to graph something like f of x equal to, sure, I'll make it e to the x times cosine of x. And we're going to find all the maxima and minima. Something to be aware of here. Just big picture graphing. We know that y equals e to the x on its own looks like this. Oh, this is actually, this question, I will say, this is a really good thing to maybe kind of remember when you're taking 17C, because we kind of talked about how when you have a function that's growing or getting smaller, and then you kind of toss in a sine or a cosine, how it just kind of makes it oscillate, but still sticks around kind of what it is already equal to. So I don't know exactly what's going to happen here, but what's probably going to happen is we're going to get something like when we multiply this by cosine. Well, cosine, what's the biggest value cosine can ever have? I think I heard someone say it. Yeah, and what's the smallest? Right. So if we're taking this function and at some places multiplying it by as much as 1, or some places multiplying it by as little as -1, you're essentially going to, in fact, here's my best guess at what the graph is going to look like. So I'm going to draw some asymptotes like you've maybe never seen before. Here's one of the asymptotes, y equals e to the x. Here's my other asymptote, the reverse of the negative, not reverse is a bad word to use there, y equal to negative e to the x. And what's going to kind of happen, and I'm just going to freehand this, right? I'm not trying to draw it really specifically right now, but I know that e to the x times cosine is kind of just going to bounce back and forth between these two things. So when I draw this, it's going to look something like, and again, I know that cosine of 0 is 1. I've kind of set myself up for failure here. Oh, well, it's going to kind of do this deal, I think, because I know that it's going to kind of mirror e to the x, but it's going to be less than it sometimes, or bigger, or bigger than e to the negative e to the x sometimes. And just so that we can kind of verify what we think this is going to look like before we even do anything else, let's go ahead. Let me change how I'm sharing just so I don't leave the people on Zoom out of it. Let's just share the entire screen here. Yeah, cool. Let's get a new window here. Oh, I'm still exploring the web work thing, by the way. And someone asked about like assignment work problems. I'm working on that. It is a little more challenging than I thought it was going to be. So I still haven't figured out how to get logged in exactly yet, but it's in the works. So let's do this here real quick. So we graph something like this just to kind of, it's never hurts to graph something in Desmos, just to kind of get an idea of what it's going to look like. So this might not look like I said it was going to look, but if you zoom out, whoops, if you zoom, wow, it looks really gigantic, right? But if you throw in an e to the x, you can see it's a boundary for it. Now, one way to make this look maybe less terrible is to kind of scale it down a bit. So I'm just going to do something to make it look nicer. I'm going to multiply it by like, I don't know, 0.0001. Same deal here, just to make it look a little bit more. It's still, I mean, e to the x grows exponentially, right? It gets out of control real fast. But you can kind of see you can see if I minimize this for a second. The thing I've drawn here kind of has the same idea. Obviously, I drew a little more exaggerated over here and a less exaggerated over here, but still has the right flavor. So how do we find the things? Well, we want to find all the maximum. I mean, we need to find the critical points by taking the derivative and setting it equal to 0. So let's do that. So, like, for example, the way I've graphed this is where a critical point should be. This is where a critical point should be. This is where a critical point should be. Everywhere where we have a relative maxima or a relative minima, that's where we're going to have a critical point. And I'm moving things around here. Let's get that back on the big, yeah. Sorry, let me move this picture of me. All right, so our function is e to the x times cosine of x. The derivative is product rule. Derivative e to the x is e to the x. The derivative e to the negative x is e to the negative x times -1, just for reference. Leave cosine alone, add, and then you reverse it, or what's a better word I'm looking for here? Oh, vice versa. That you do the vice versa, right? You do the opposite thing to the opposite things. So e to the x, leave it alone. Derivative of cosine of x is negative sine of x. And then to find the critical values, you set that equal to 0. I'm going to factor out an e to the x. I'm left with cosine of x minus sine of x equal to 0. And then he gives you a trig identity I've actually never seen before. Totally fine. You could definitely use that, but you don't actually have to use that to solve this. So if you're trying to solve this equal to 0, you're really just looking for either e to the x equal to 0. That has no solutions, right? E to the x is always greater than or equal to, greater than, not equal to, greater than 0. It's never equal to 0. Or the other factor, cosine of x minus sine of x equal to 0. So really all you're trying to do is find where cosine of x is equal to sine of x, which if you're relatively familiar with your unit circle, you probably know. If I look at my unit circle for a second here, that's okay, not the best. The radius is 1. That's why it's called a unit circle, because unit means 1. And sorry, my unit circle's there. That looks a little bit better. And the x coordinate is the cosine value. The y coordinate is the sine value. So right here at an angle of 0 radians or 2 pi radians, we can see that cosine of 0 is equal to 1 and sine of 0 is equal to 0. Up here at pi over 2 radians, we can see that cosine of pi over 2 is equal to 0 and sine of pi over 2 is equal to 1. And literally, I know it might have been a while, but literally the point on the circle, the x coordinate and the y coordinate, gives you the cosine value and the sine value. So if we're looking for the place where sine and cosine are the same, because that's what we're looking for, where sine of x is equal to cosine of x, we're looking for the coordinate on the unit circle where what two things are the same? X and y. And we know where x and y are equal to each other. It's on the line. Y equals x. Y equals x, which makes what angle with the x-axis? Yeah, I see you mouthing it over there, but not wanting to say it out loud. Exactly. 45 degrees or pi over 4 radians. So that is one answer to the question, where does cosine x minus sine x equal 0? One angle is going to be pi over 4 radians. You do need to give your answers in radians here, because otherwise we don't graph with degrees on the x-axis. And then also, if you go a full, I should say a half revolution around, you also get a place where sine and cosine are equal to each other. So right here, sine and cosine are both equal to positive root 2 over 2. Over here, both sine and cosine are equal to negative root 2 over 2. So pi over 4, and then pi over 4 plus pi over 4 plus pi is 5 pi over 4. And then you can just keep adding pi. So another angle would be 9 pi over 4. Another angle would be 13 pi over 4. And unfortunately, the question as it's phrased doesn't give you like a limited domain. So you kind of have to, in some way, express all of these critical points. Now, what's going to happen here is this function is kind of periodic, meaning it's going to kind of repeat itself after every 2 pi, except the e to the x is going to make it so it gets more oscillating, but still it's going to kind of repeat. So how do I figure out where I have my maxes and my mins? I place these critical points on the x-axis. Oh, I should point out, sorry, on the number line. I should point out you also could have solved this by taking that interesting trig identity the square root of 2 times cosine of x plus pi over 4. And setting that equal to 0. And then cosine is equal to 0 when the angle is pi over 2, or 3 pi over 2, or 5 pi over 2, or 7 pi over 2, or some odd multiple of pi over 2. So if you want the angle x plus pi over 4 to equal pi over 2, sorry, x plus pi over 4, sorry, to equal pi over 2, that's going to give you x equal to pi over 2 minus pi over 4, which is pi over 4. Or if you want the angle x plus pi over 4 to equal 3 pi over 2, you're going to get x equal to 3 pi over 2 minus pi over 4, which is going to be 5 pi over 4. So you get the same results, just in a different way. Either way is totally fine. I would never know that trigger. Like that trigger identity just seems incredibly bizarre to me. So I have no idea that that's there. I would just say, I know how to figure out when cosine and sine are equal to each other, which is nice. It's maybe no, I take it back. I didn't even say it, I take it back. So I'm going to put some of these points on my number line here. Not all of them, because obviously I couldn't do all of them. I might even go 1 to the left and say pi over 4 minus pi is negative 3 pi over 4. And then I would look at what my derivative is doing. Okay, so here's my derivative. I'm going to pick something between 5 pi over 4 and 9 pi over 4 to see if my derivative is positive or negative. And I'm going to pick the easiest thing I can think of, which would be 8 pi over 4, because that's 2 pi. A nice even multiple of pi is easy. So if I plug in 2 pi, f prime of 2 pi, let's see, e to the 2 pi is positive. Cosine of 2 pi is 1. Sine of 2 pi is 0. So you're going to get a positive number times 1 minus 0, which is positive. I don't actually care that it's equal to e to the 2 pi. I just care that it's positive. So over here, it's positive. If we pick something between pi over 4 and 5 pi over 4, like pi, and I plug that in, then cosine of pi is negative 1. Sine of pi is 0. So then that's going to be a negative in there, and a positive number times a negative number is a negative number. And at this point, you can probably guess that every time we go to a new interval, it's just going to change signs. Because between here and here, I can pick pi. Between here and here, I can pick 2 pi. Between here and here, I can pick 0, negative pi, negative 2 pi, negative 3 pi. So I'm just going back and forth between this point and this point. And at this point, cosine is bigger than sine. And at this point, cosine is less than sine. So anyone where the angle is a multiple of 2 pi, you're going to get a positive derivative. And anyone where the angle is an odd multiple of pi, you're going to get a negative derivative. So what does that mean for us? If the derivative is positive, what does that mean about the original function? Let's see. So when the derivative is positive, that means like the slope of the tangent line is positive. So you've got like a tangent line like that, which means the function getting bigger or smaller? Or a tangent line is positive slope. Bigger. So when the derivative is positive, the function is they said that's where it's negative, sorry. When the derivative is positive, the function is increasing. When the derivative is negative, the function is decreasing. Like that. So for this example, we can see that we have a relative maximum when x is equal to, well, right here we have a relative maximum because the function was getting bigger, and then after pi over 4 was getting smaller. So a relative maximum when x is pi over 4, and then 9 pi over 4. And then the next one would be another 2 pi later at 17 pi over 4. And then the minima, the relative minimums are going to be when x is the other value. So when it's going from decreasing to increasing. So at 5 pi over 4, we'd also have one over here at negative 3 pi over 4, which I should have listed first. Let's just make that a negative 3 pi over 4. 5 pi over 4. The next one would be another 2 pi more, which would be 8 pi over 4 plus 5 pi over 4 is 13 pi over 4. And the list never ends, unfortunately. An easier way to write it would be x is equal to pi over 4 plus 2 pi times k, where k is an integer. So pi over 4 or anything that has the same is a coterminal with pi over 4, you're going to get a relative maximum. Similarly, here we could write x equal to negative 3 pi over 4 plus 2 pi k. So that's where your relative extrema occur. So then you can go back to your graph and try to make it look a little bit nicer. So, okay, well, here we go. Trying our best here. So we know that we're going to have one of the things I would actually include in this graph is cosine is going to be 0 at every odd multiple of pi over 2. My cosine is 0 there and down there and there. So if I start marking things off here, and it's going to be a little bit gross, but just to kind of get an idea here, if that's like pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, negative pi over 4. So I know that cosine is going to be 0 at all the pi over 2, so I'm going to get a 0 there and there. No, not there. Sorry, all the odd, not there. All the odd multiples of pi over 2. So it's going to hit there and there. And then I know at, gosh, 5 pi over 4, I have a relative minimum. So it's going to be something like down here. And at pi over 4, I have a relative maximum. And at negative 3 pi over 4, which is way over here, I'm going to have a relative minimum again. So it's doing something kind of like this. And then I'm going to hit that point up there. Yeah. And then down there. Oh my gosh, this is hard to graph. Now my y values are not great, right? I didn't even check to see what, like, I'm just saying this is whatever the y value is whatever the y value is. But that's an idea of what part of it looks like. I don't know how much you really have to graph, because you obviously can't graph the entire thing, because it just keeps doing this same sort of thing where it's going to go, right? When we go to the next one, it's going to come, back down, and it's go back up. And then every pi over 2, you're going to hit a 0. Every odd multiple of pi over 2, you're going to hit a 0. And then you're going to have your relative extrema at the pi over 4s or whatever they are. It's not an easy graph, for sure. Certainly, if it were me as a student, I might take a look at Desmos and be like, let me kind of see exactly where those intercepts are occurring. Now, I wouldn't try to draw the graph like it looks on Desmos, because I think it's not very helpful. I would draw it more like I have drawn it here. Questions about this kind of terrible graph? I will mention this is not the same as the homework problem, but it is very similar to the homework problem. Your homework problem is a little bit different, because your homework problem, it's e to the negative x times sine of x. So it's actually going to get smaller from left to right as opposed to larger from left to right. And I think you're going to end up having different intercepts, because you're going to have intercepts when sine is equal to 0, which is when x is a multiple of pi, instead of when cosine is equal to 0. So just be aware, it's a little bit different, but not that different. It's not my favorite problem ever, but that's okay. Other questions from, so yeah, I don't want to spend too much time on, actually, I know I've asked like 20 times already. Who all is in Goldsmith's class? Okay, a few people. So that's totally fine. And I'm sure he's not gonna like skip the stuff we're talking about currently. So you're gonna get there. I'm just gonna be working a little bit ahead of you all for the moment. But are there any other specific questions from the Goldsmith class before we move on to talking more about integral stuff? And it's totally fine to have questions, even though there's only a few of you. Like, it's good for everyone to see this. Being able to graph this is a useful skill. It's not just for the people in that class. So, oh, chat, thank you, appreciate it. Yes, that's all. If you see something, let me know. Shouldn't the 0 be a point 2? Good question. Cosine of 0 is 1, so I don't think it's actually a point of note. I mean, I could certainly find it. Like, I suppose if you're looking at my original function, which was, sorry, let me move this here, apologies, which was e to the x times cosine of x. If I plug in 0, I do get e to the 0 times cosine of 0, which is 1 times 1, which is 1. So you could note that is the point. So I could have marked that as like 1. That is like 2. So it is noteworthy in that it's a nice value, but it's not it's not an x-intercept, it is a y-intercept, of course, you're setting x equals 0, and it's also not a relative extrema, right? Because our relative extrema, if we look back here, we had relative extrema at a relative maximum of pi over 4 and a relative minimum before that at negative 3 pi over 4, but there isn't a, sorry, negative 3 pi over 4. But there is not a relative max or min at x equal to 0. Now, I should say for the other one, right, for e to the negative x times sine of x, you will get the intercept of 0, 0, which is notable, I would say. Cool. All right. I don't love standing in the dark up here, but I do feel like the quality of the picture is better, so I can just deal with that. More integral stuff. So area under a curve. Still, for a while. Let's see here. So here's a good question. Should we do more examples where we use the limit definition to calculate the area under a curve? They're not my favorite. They're no one's favorite. But I think we should do that one more. So let's do the following example. We want to find or evaluate the integral from 0 to 1 of x squared minus 1 dx using the limit definition. And I promise you, as soon as we can, we will move away from the limit definition and start talking about the fundamental theorem of calculus. But there's a few things we have to build up before we can really do that. So let me words. Can I speak the words? Sure. So let me draw a picture here because I want to point something out. So f of x equal to x squared minus 1 is an upward opening parabola. And it has a y-intercept of -1 and an x-intercept of +1 and also -1, but I only care about being between 0 and 1. So my graph kind of looks like this. And I'm looking at the area in here. And what's going to end up happening here is we're actually going to get a negative answer. So even though the area itself, we only think of areas being a positive value, when you have a region that is under the x-axis, we think of that as being a negative value, because when we're talking about area, what we really mean is the net area that is under the curve and above the x-axis. So if your curve is below the x-axis, you're going to end up getting a negative value for that, which is totally fine. Just good to know what we expect is going to happen. So, all right, let's go ahead and write up the limit definition of this integral, of this area. And I should be super explicit here. I just want to remind you of what all this means. When you write this integral symbol from 0 to 1, it just means the area, the net area under the curve, under this curve above the x-axis that is between x equals 0 and x equals 1. So this thing I've shaded right here. And we could draw some rectangles. There's your x1. There's your x2. I'm using right endpoints, as we often do. So if I'm going to write this using the limit definition, we're going to start off with a limit. It's the limit as n goes to infinity of the sum from I equals 1 to n. And even though we're going to have to work this out in a minute here, there's actually a very nice shorthand here. What's going to go in here is just your function evaluated at x sub I. Your x sub I is the right endpoint. And so I should point out that f of x sub I is just the rectangle height. Okay, to find the area of each individual rectangle, you're going to take the height and multiply it by what? How do you find the area of a rectangle? It's height times base. And the base is what we typically call delta x. There's our base right there. So now our job is to fill those things in with what they actually are. So there are three things to identify here. Delta x is always just the width of each subinterval. And I know we probably didn't cover this super clearly, but how many subintervals are there? There's n, right? That's why we're adding up all the rectangles from I equals 1 to n. If you actually wrote this out longhand, this would be the limit as n goes to infinity of, well, when I equals 1, I get f of x sub 1 times delta x. And when I equals 2, I get f of x sub 2 times delta x. And when I equals 3, I get f of x sub 3 times delta, all the way to the last one, which is when I is equal to n. So you get f of x sub n times delta x. So there are n subintervals. I know I didn't draw them all. The very last one here, though, right? If you wanted to do it, okay, that would be like your x sub n minus 1 right there. And right there, your last rectangle, which is going to have a height of 0, would have the right-hand endpoint being x sub n. So there are n, well, technically n plus 1, x values, and there are n subintervals. There are n rectangles we were adding together. Okay, so our delta x is just the entire length, 1 minus 0, divided by the number of subintervals. More generally, that's your b minus a over n. That's your b value, that's your a value. So that's just going to be a delta x of 1 over n. Your x sub I. There's a very nice way of knowing what x sub I is. It's going to be your a value plus I times delta x. In this example, our a value is 0. And delta x we just found to be 1 over n. And instead of writing this as I times 1 over n, I would just write it as I over n. So our x sub I is just I over n. Here's a nice check to make sure you have found the right x sub I. Let me ask you all a question. Looking at my picture here, I know I haven't labeled it very well, but what value should x sub 0 actually equal? Yeah, 0. Now let's see if I actually plug in, so x sub 0, if I plug in 0 for I get 0 over n, which is 0. In a similar way, x sub n is the right end, I don't know, that is the right, gosh, I can't think of the words. It's the right endpoint of our interval, which is 1. So if you actually plug in n to what x sub I is equal to, we're going to get n over n, which is 1. So if you've got the right formula here and you find x sub 0, you should actually get your a value. And if you find x sub n, you should actually get your b value. So if you're not 100% confident about that, it's a really easy way to check that you've got the right thing or not the right thing. And then you can go back and kind of fix it. And then finally, our function is just the thing we're integrating. It's just the thing we're finding the area under being relative. So our function is x squared minus 1, and our f of x sub I is, I'm just substituting x with I over n. So it's I over n squared minus 1. Now we have all the pieces so that we can do the terrible algebra. Questions about anything I've written here or anything I can clarify? I know my writing is, I think you can hopefully see most of what I'm writing there pretty clearly, I think. If you can't, you should ask for clarification. I'm always happy to explain anything. All right, so keep some of this on the page here. We're going to take this limit here and we're going to fill in all the pieces. So our integral from 0 to 1 of x squared minus 1 is equal to the limit as n goes to infinity of the sum from I equals 1 to n of, okay, f of x sub I is I over n squared minus 1, and delta x is just 1 over n. Cool. I will say a lot of the time when you get asked questions about this process, you're just asked to actually find what the limit expression is and then to stop. A nice question is find the limit definition of the integral, but don't actually evaluate it. And we'll do that a couple times too, because I think that's some good practice. So now we're going to do the math. which involves a formula that we haven't talked about yet, but I will totally tell you what it is. So we're just going to multiply this out. We're going to get the limit as n goes to infinity of the sum from I equals 1 to n. I over n squared is I squared over n squared. And if I distribute the 1 over n, I get I squared over n cubed. And then 1 over n times -1 is just minus 1 over n. And I'm seeing the thing that I always look for when I do this kind of problem, which is that every fraction should have a power of I on top that is 1 less than the power of n on the bottom. I to the second, n to the third, I to the 0th, n to the first. So I'm good to go. I'm going to break this up in the following way. I want to write it as however many summations of however many pieces I have. So it's going to be the sum from I equals 1 to n of I squared over n cubed minus the sum from I equals 1 to n of 1 over n. And then I personally like to pull out anything that's not I. So what I mean by that is any constant multiples. And as far as the sum is concerned, n is a constant. In this summation, n is just the last number, whatever that happens to be. It's not changing. If you ignore the limit, which we're ignoring. So then what we're going to do is we say this is equal to the limit as n goes to infinity of, I'm going to write this as 1 over n cubed times the sum from I equals 1 to n of I squared minus 1 over n times the sum from I equals 1 to n of what's left here if I factor out a 1 over n? Or divide out a 1 over n. I know you know. And you just don't want to say the words because it's embarrassing to talk in front of everybody else. Okay, show me on your fingers, not that finger, please. Yeah, thank you. That many. 1. We're left with a 1 there. So, not that finger. So now we're going to use our rules. Now, I haven't told you what happens when you add up all the squares. So quick aside here. There isn't a nice slick way of showing this like I did last class for the 1 plus 2 plus 3 plus 4 all the way up to n. So I'm just going to tell you what it is. And I might tell you something else really cool, depending on if we have time. So that's 1 squared plus 2 squared plus 3 squared plus 4 squared plus all the way to n squared. And it's equal to n times n plus 1 times 2n plus 1 divided by 6. Do you need to know that? Probably not. I should say, do you need to memorize that? Probably not. Do you need to know it? Maybe for a little while. So now, and then of course, just as a reminder, the sum from I equals 1 to n of just 1 is 1 plus 1 plus 1 plus 1 plus 1 n times. So that's just n. So here's what we've got. This is going to end up being equal to the limit as n goes to infinity of 1 over n cubed times n plus 1 times 2n plus 1 over 6 minus 1 over n times n. And I don't really want to do too much algebra here. I really, really, really don't want to multiply out the top here. It's not impossible, it's just annoying and not necessary. So let's do one simplification here. I'm going to write this as the limit as n goes to infinity of n times n plus 1 times 2n plus 1 over 6n cubed. Yes, I know I could cancel one of the n's really easily, but I don't want to. Minus 1. So now let me ask everybody. What is the highest power of n in the denominator of this expression? I know that's a dumb question, but what is it? Show me on your fingers. Yeah, that many. Thank you. Yes, 3. Cool. What's the highest power of n in the numerator, even though I didn't multiply it out? Also 3. It is also, so, because if you look at this, if you do, so n plus 1 times 2n plus 1, you get 2n squared plus other lower powers of n. And then if you multiply that by n, you're going to get 2n cubed plus other lower powers of n. And what should always happen with this kind of problem is once you get to this stage, the highest power on top and the highest power on the bottom should be the same. Which then means we have a really easy way of evaluating the limit as n goes to infinity. I know that when I take a limit as n goes to infinity of something times n cubed over something times n cubed, plus smaller terms that don't matter, You just get the coefficient on the bottom. And what's the coefficient on the top if I were to multiply that out? It's not 1. It's a little bit more because I have an n times a 2n. So on top, I'd actually have a 2n cubed, which means I'd have a 2 over 6 minus 1. If you did multiply this out, again, I don't want you to have to multiply it out because it's not necessary, but I'll just point out that this part here would be the limit as n goes to infinity of, if you actually multiply this out, you get 2n cubed plus 3n squared plus n all over 6n cubed. And then you'd be like, oh yeah, highest power is on the same on the top of the bottom, so that means I can just take the quotient of the leading coefficients, which is 2 over 6. Yeah.
I'm confused how you got the 6n to the third power in the denominator in the first place.
Like from here to here?
Yeah.
So all I did there was when you have a fraction times another fraction, we multiply the top, right? That's a 1 over n cubed times and n times n plus 1 times 2n plus 1 over 6. Now is it cool?
Yeah.
Cool. So we end up getting 1/3 minus 3/3, which is negative 2/3. And that's our actual answer for the net area under this curve that's above the x-axis. Now, if someone asked a slightly different question, if they said how much area is between the x-axis and y equals x squared minus 1 on the interval from 0 to 1, the technically correct answer would be positive 2/3 because the amount of area should be a positive number, whereas a definite integral can end up being negative or positive. Okay, what time is it? That clock is hard to see. Oh, wow. Yeah, it's really hard to see. I thought I had way more time. Okay, so let's talk about some properties of integrals. Yeah, that's a good idea. So, some properties of integrals. Let's see, where'd you go here? Yeah. So, yes, a couple things to be aware of. I don't love doing. Sorry, there's like 1,000 things to say and 15 minutes to say them in. So I'm gonna try not to rush myself here. We have Friday. We've got all sorts of time, so we'll say what we can say here. So a couple things to know about when you're calculating integrals and you're finding them is some stuff that might seem pretty familiar. Like if you do the integral from a to b of a function added to another function, you can just split them up like you think you should. Meaning the integral from a to b of f of x plus g of x dx is just the integral from a to b of f of x dx plus the integral from a to b of g of x dx. I think of this as being very similar to a derivative property that we have. If you take the derivative of two things added together, you just take the derivative of each part and add them together. And in a similar way, instead of writing a whole nother line, it's also true if you subtract the functions. So the integral from a to b of f of x minus g of x is the integral from a to b of f of x dx minus the integral from a to b of g of x dx. Also, just like with derivatives. So when you're adding functions or subtracting functions, you can just differentiate or anti-differentiate, I should say integrate, them separately, and then add or subtract the results together as sensible. Also, like derivatives, you have a constant multiple property. So I'll remind everybody, so in fact, I'll remind everybody over here, the derivative of f plus or minus g is just f prime plus or minus g prime. Right, that's the similar derivative rule. We also have a constant multiple rule. If you're finding the integral of a constant k times a function f of x, you can pull that constant out in front. And it's the constant k times whatever the integral is. That property we use a lot. Like that's almost always you go to. Like if you've got like 4 times some gnarly function, just pull the 4 out so you don't have to worry about it until the very end. And to go along with the theme here, we definitely have the similar thing being true for derivatives. The derivative of a constant times a function is just equal to that constant times the derivative of that function. You use this all the time. The derivative of 6x to the third, we all know it's 18x squared, but the process that you're never really using is you're saying, oh, that's really 6 times the derivative of x cubed, which is 3x squared. And then you're multiplying the results together and getting 18x squared. You're using that property every time you do this. You just don't always think about it, which is normal. You shouldn't think about it really. What other properties do I have here? Oh yeah, that one. So if you do the integral from a to a of some function, so you're saying how much area is under the curve f of x when you start at x equals a and you end at x equals a? You've got no width, meaning you've got no area. It's gonna be a big old 0. Couple more. This one I think is always kind of weird. The integral from a to b of f of x dx. If you change the order of the limits of integration, that changes the sign of the integral. So when you integrate from left to right, you kind of think of it being normal. And you get like, if your curve is above the x-axis, you get a positive area. But if you integrate in the opposite direction from right to left for a curve that's above the x-axis, you actually get a negative answer. And it's kind of because things have to work that way. The last two, sure. So this last one is, yeah, so the last one's a little tricky. So, so for example, this is going to look kind of silly. Here's my function f of x, nothing in particular. But if I want to find the area under it from a to a, well, the area under the curve between a and a, I've got a line. And a line is a one-dimensional, right? One-dimensional, yes. It's a one-dimensional shape, doesn't have any area. Now, this other thing. So that thing is more complicated to explain, but it's not impossible. So why is it true that if we're thinking, so now I'm going to throw in a b here. So the integral from a to b, okay. I would not recommend writing this down, personally. You are certainly welcome to, but it's going to get a little bit technical here, and I don't want you to weigh you down with all that, really. So here's the deal. When you calculate this, it's the limit. Doing it the long way, the limit as n goes to infinity, sum from I equals 1 to n of f of x sub I times delta x, and delta x is b minus a over n. Which in this example, the way I've written it, b minus a is certainly positive because b is larger than a. Cool. So now let's take a look at this. If I did the integral from b to a of f of x dx, it's the same sort of deal. You're just taking the limit of the sums of all the areas. But now, using the same sort of thing, it should really be a minus b over n. That's my delta x. But a minus b is negative. In fact, look, I can actually rewrite this as the limit as n goes to infinity of sum from I equals 1 to n of f of x sub I times, if I factor out a -1 from the top here, I've got a -1 times b minus a over n. But then I can pull that -1 all the way out in front of this entire thing. This is really equal to -1 times the limit as n goes to infinity of the sum from I equals 1 to n of f of x of I times your b minus a over n. But look, that's exactly that. And so this is equal to -1 times that, which is equal to that. It's kind of funky, but it is true that when you interchange the order of integration, you change the sign of the original integral. So if you ever want to switch a and b, you're certainly welcome to do that. Just make sure that you slap on a negative in front of the whole thing. It's kind of nice. It actually is really convenient sometimes. And then let's look at finally my favorite, not my favorite, but another interesting property, which I'm going to go back to this other page here just so I can have them all on the same page here, is that the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of x dx. So basically, you can break an integral up anywhere you want. So if I want to go all the way from A to B, well, first I can go from A to C, and then I can go from C to B. And fun fact, you might think C had to be between A and B, but it doesn't have to be between them. It can be anywhere, which is kind of cool. Let me show you what I mean. I think I might have a cool example here. Except it's hiding from me, so. Yeah, are you over here? Where? I lost it, it's fine. So here's what I mean. So graphically, I think it's not too terrible to see this. So if I'm going to break this up at some, I'm really smearing this around here, sorry. Again, when you're talking about integrals, we're just talking about area under a curve. That is really, 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 at least I should say, when we're talking about definite integrals, we'll talk about indefinite in a while. When you're thinking definite integrals with limits of integration, I really want the first thing you think of to be what? Area under a curve. Thank you. That's exactly it. So when I see something like this, the integral from A to C of f of x dx, I'm just thinking, oh, that's the area under the curve from A to C. I should say the area under the curve f of x from A to C. So that's the green part. And then if I add on the integral from C to B of f of x dx, well, that's just this other part, which I'm going to color red. But the red part plus the green part is just all the area under the curve from A to B. So that is totally equal to the integral from A to B of f of x dx. All the area. The green and the red. Question. I did say that. Excellent observation. So let's see what happens if we move C to the side. Good question. Glad you're paying attention. So let's say we have it now like this, where you have A, B, and C. Ooh. All right. So this equation is still true, but I'm not going to maybe label things in the exact same way. So what I'm saying here is the integral from A to B of f of x dx should equal the integral from A to C, which is all the area, right? The integral from A to C is all the area. All of it. I'm going to call this the red part. And now let's notice here, the rest of it's going to be the integral from C to B, which is backwards of how you would normally think of it. So what I should really do is I should say, well, this is the same as integral from A to B of f of x dx equals the integral from A to C of f of x dx minus the integral from B to C of f of x dx. And then it makes total sense that the red part is equal to the black part minus what I'm going to color in as the green part. That makes some sense. That, in fact, it kind of shows why we need that switching of the order of limits of integration to work the way it does work, so that this thing is still true no matter how we write it. It's kind of cool. I think it's actually really neat, to be honest. So, all right. Let's do, yeah, we got time. We got 5 minutes. Okay. Also, just as a reminder, make sure you fill out the attendance form at some point. So let's do one more thing, because I think is nice. So let's say somebody asked you, I'm going to make it a little bit more challenging than usual. Let's say someone said, I want you to find the integral from, sure, -2 to 4 of the square root of, yeah, making it hard. Sure, sorry, one second here. 3. Oh man, now I've like forgotten what I was trying to make it fun, and now I've blown it. Let me write something down real quick here. 3 squared plus 4 squared equals, sure, okay, cool, I got it. We're good. Right on. So we want 9 minus x minus 1 squared. And I will tell you, you will never learn in this class how to actually do this using the fundamental theorem of calculus. There is a way using methods that are not taught in this class to actually anti-differentiate this function and then plug in the endpoints, but that's not what we want to do here. We want to use geometry. So let's look at this function for a second. Let's look at y equal to the square root of 9 minus x minus 1 squared, which I've definitely written the kind of more misleading way than this question is usually written. I'm going to write you an easier one in just a minute here. So let's square both sides. And then let's bring the x minus 1 squared over to the other side. So we have x minus 1 squared plus y squared equal to 9. And this equation is the equation of what kind of shape of graph? Yeah, okay. I tried to make a circle. It's like the clock. This is a circle. I know, right? I know. Right? Okay, circle. Okay, sure. It's not the YMCA over here. So circle. What's the center of this circle? What's the x coordinate for sure? 1, and the y coordinate is, it's always confusing when they didn't write something there, but that's really like a y minus 0. The y coordinate is 0. And I meant to write center, not circle. And the radius is what? Square root of 9, which is 3. Okay, so now look at what we can do. We can graph this circle. Well, really, I should point out, this is the equation of the entire circle. If you have y equal to the square root of some stuff, y has to be positive. So this is really just the top half of that circle. So what we really have here, things, bless you, that we have graphed, or that we're going to graph, is a circle centered at 1, 0 with a radius of 3. So we go 1, 2, 3 to the right, 1, 2, 1, 2, 3 to the left, and 1, 2, 3 up to get your thing that kind of looks like a circle. So now look, my question is exactly matching up with what I need to do here. I'm trying to find the area under this curve between x equals -2 and x equals 4. In other words, I'm trying to find the area of half a circle with radius 3. Well, great, that's not too terrible at all. That area is going to be equal to 1/2 times, what's the area of a circle? Or the formula for the area of a circle? Pi r squared, and my radius is 3. So it's 1/2 times pi r squared, which is going to be 9 pi over 2. And that is how you were expected to actually do a problem like this. So a more typical way of writing a problem like this, which is a little bit less hard, is if someone writes it like the integral from 0 to 5 of the square root of 25 minus x squared. It's a little more obvious that y equal to the square root of 25 minus x squared is the top half of the circle. And I know we're out of time here. Here's the last thing I'll say. So for this one here, the area of this, so this circle has what radius? Anybody? Yeah, that many, exactly. Yes, this many, 5. So the area under this curve would be not 1/2 pi times 5 squared, because you're not getting the entire semicircle, because you're not going from -5 to 5. You're only going from 0 to 5. So you're only getting 1/4 of the circle. So here the area would be 1/4 times pi times 5 squared. And it really helps if you draw it. If you actually draw this out, the circle goes from -5 to 5. I should say the semicircle really, but then we only want this part of it that goes from 0 to 5. So, oh yeah, that's 1/4 of a circle. And so you just say, oh, it's 1/4 of pi r squared. All right, that is all I have for today. We will continue talking about area under curves on Friday.